Hello everyone, hope you're doing well. Thank you for joining AWS Summit Online and welcome to this session. We are really excited to be here and sharing with you regarding event-driven architecture and how to implement with AWS. So for today, we will talk about the concept and implementation of event-driven architectures. And we think this is really important because we have seen that more customers are adopting the event-driven architecture, but the most important thing is the implication. Event-driven architecture makes their team so much more agile and so much easier to build scalable, reliable, and resilient systems. My name is Donnie, a senior developer advocate working for AWS, and let's get into it. Here is the agenda that we're going to talk through today. We structured this session by starting off with an introduction to event-driven architecture to lay a foundation on what is event-driven architecture and to give you motivation on why you need to start to adopt if you haven't. The discussion will be around some key challenges on event-driven architecture, and that will be a good segue for us to introduce Amazon EventBridge. We'll cover how you can use EventBridge with various design patterns and what are the other AWS services that can help you to make an agile, scalable, and resilient system. And for sure, we're going to do few demos for more better understanding on how to implement event-driven architecture with Amazon EventBridge and other AWS services. So what is an event-driven architecture? The idea behind event-driven architecture is to build a decoupled systems that run in response to events. An event-driven architecture uses events to trigger and communicate between decoupled services and is common in modern applications built with microservices. An event is a change in state or an update, like an item being placed in a shopping cart on an e-commerce website. Events can either carry the state, such as the item purchase, or events can be identified like a modification that an order was shipped. Event-driven architectures have three key components: event producers, event routers, and event consumers. A producer publishes an event to the router, which filters and pushes the events to the consumers. Producers and consumer services are decoupled, which allows them to be scaled, updated, and deployed independently. Now, the next question would be, why do we need to choose an event-driven architecture? If you've been to an AWS conference before, you've probably seen a slide like this. And let me iterate why people are moving to microservices. Most of us started with monolith, and most common reason why we choose monolith is because it's relatively easy to build. And there's definitely nothing wrong with that. It's way simpler to understand how the system is going to work when all your data is in one ASIC-compliant database, and all of the calls you're making are operating against the same memory space. However, the more our business grows, we have more users. We have add new features, the more complex our system becomes. It's inevitable. And one of the solutions to handle this kind of challenge is to build a distributed system. Distributed systems of microservices are way more complex, but the problem is monoliths don't scale. If you have big complex systems and you want to be able to effectively leverage dozens of hundreds of engineers to build features in parallel, you have to move to the microservices model. So in our journey building the system, we'll eventually need to make our system more agile, scalable, and faster. And it's pretty much aligned with Conway's law, which stated that system design is largely influenced by the organizational structure of the teams that build the system. And this is one of the reasons why customers are moving to microservices, because they grow with rapid pace. When we are talking about modernizing our applications in this context with microservices and event-driven architecture, it always circles back to how we can fully leverage cloud-native computing, and it makes sense to do that. And this is the pattern that supports high-speed innovation and one of the pillars on how Amazon.com successfully transformed into microservices in the last decade. There are three core architectural patterns. There are APIs, events, and data stream. And with this kind of paradigm, components in our system is loosely joined by APIs, and events and data flows are able to grow in different directions. As a result, it allows us to do more experiments, which leads to innovation. We've discussed in a quick overview level on event-driven architecture, microservices, and cloud-native computing, and how they can work together. Now, let's illustrate on our journey to implement all of these components as our system grew. Let's assume that we are building an e-commerce application. We have order service to process service and invoice service to handle payment from our users. This is a really standard synchronized API-based service. In this case, when a client makes a request to the order service, it has to make downstream requests to the invoice service. And once it gets a successful response, it can respond back to the client with a success message, provide the confirmation number for the customers, and everything works well in this case. With this synchronized API-based service, what happens when we start adding a couple of more services and we need other services to integrate with your order service? It becomes like this diagram. With order service is calling downstream requests to invoice service, fulfillment service, and forecasting service. And this is totally normal. As what we know, as our system grows, we need to add more features and the data flow is totally unexpected. But what is problematic about having a synchronous API design is that the order service needs to know everything from other services. Order service needs to call of this downstream request before returning back the response to the users. And what happens if one of these downstream services has a hiccup? Well, in the worst case, we get our system acts really slow and we'll return timeout error to the caller. And in this case, nobody's happy. Order service is not happy, our customers are not happy, and we are not happy. Even if we have implemented this system as a microservices, it still poses a few challenges. We talk a lot about how great microservice is, and back to our tenet is we build microservice to have scalable and agile system by decoupling these services. But the order service still needs to know and locate each of these other endpoints for these services, as it needs to understand how to make the appropriate API calls. This is when we need to have a service discovery and our system becomes more complex. And also, what to do if one of these services fails. We need to have appropriate retry logic and error handling. While we can do vertical scaling for our cloud resources, but over the longer term, we want to add more and more services to process the data, look up query, update stocks, send to other third-party services, and each time that the order service needs to do that, it is highly coupled to the other services. Let us show you in real-life implementation how this kind of challenge could happen to any of us.
This demo is designed to illustrate the architecture shown on the screen. We have an order service, serving requests via HTTP API. To complete the request, the order service needs to make downstream calls to 3 services. They are invoice service, fulfillment service, and forecasting service. Once that the order service receives responses from all services, it will return back the response to the client. We are going to use Amazon API Gateway and AWS Lambda for this demo, and the idea is to illustrate the challenge of systematic calls using synchronous APIs if it's not handled properly. There are 2 scenarios in this demo. First scenario is the ideal scenario with the client calling the order service via HTTP API, and all downstream requests made by order service got 200 OK response from other services. This scenario is ideal if everything works fine. Let's take a look. We have 4 Lambda functions in this demo. There are functions for each service which shown on the diagram architecture. Nothing too fancy about the function. They only have to print out the event received into CloudWatch logs. And also we have timer there to help us simulate the second part of this demo. The order service is our main function and integrated with API Gateway, as this is the public-facing API whenever a client needs to send an order request. Now, if we click this endpoint, it will return to us all the response from other services. And if we simulate the traffic using Artillery Toolkit with 100 requests, everything is still good with all requests returned 200 HTTP status code. All good, everyone is happy. Now, for the second scenario, we're going to add some changes in one function. The idea is to illustrate what happens if one service fails to complete requests in a systematic synchronous API design. Let's assume that the forecasting service needs to process a really complex scenario and it takes 30 seconds in average to complete a single request. And let's try to simulate again the traffic with Artillery tool. We're going to use the same config with 100 requests hitting the same endpoint. And let's see what's going to happen. As you can see that all requests, they end up with 504 HTTP status code, which means the request is timeout. And this is a classic challenge in a systematic synchronous API design. And you can do vertical scaling, increase timeout in API gateway, but that doesn't solve the underlying problem. It's the design.
Now, in the long run, we might need to add more services, and our architecture now looks like this. And you might already guess it. This is an example on how we could move to event-driven architecture to handle the challenge that we discussed earlier. So instead of having all the service to call each of downstream services, it's now sending an event. For example, an order was created, and we have other services to subscribe to this particular event. Maybe not all services interested on taking any action to a particular event, maybe only one or two services. But with this kind of architecture, we are giving a freedom for those services to act independently based on the task in serving requests. Now it's great. We can decouple our system components and practically scale independently based on the demand. And the next question will be, what do we do with these arrows? In this case, we need to have event routers. To reiterate, in event-driven architectures, we need to have three key components: event producers, event consumers, and event routers. A producer publishes an event to the router, which filter and push the events to consumers. Producer services and consumer services are totally decoupled, which allows them to be scaled, updated, and deployed independently. The event router will automatically filter and push events to consumers and acts as an elastic buffer that will accommodate search in workloads and also a centralized location to select and filter events, audit your application, and define policies. And by placing event router in our architecture, we get advantages. We can transfer data between systems. We can develop, scale, and deploy service independently from other teams. We can also fan out the event without having to write custom code to push to each consumers. The router will push the event to the system, each of which can process the event in parallel with a different purpose. And lastly, event router establishes indirection and interoperability among the systems so they can exchange message and data while remaining agnostic. And what kind of service that we can use? Do we need to build one? Or is there a better option? Introducing Amazon EventBridge. EventBridge removes the friction of writing point-to-point integration by letting you easily access changes in data that occur in both AWS and SaaS applications via a highly scalable central stream of events. With EventBridge, you get a simple programming model where event publishers are decoupled from event subscribers. And this allows us to build a loosely coupled, independently scaled, and highly reusable event-driven application. It's fully managed, so it handles everything from event ingestion and delivery to security, authorization, and error handling, making it easy to build scalable event-driven application. And because EventBridge is serverless, there is no infrastructure to manage, and you can only pay for the events you consume. And Amazon EventBridge is a significant addition to AWS offerings on building event-driven architecture, giving you freedom to choose the best tool for your case. Now, there are two main types of routers used in event-driven architecture. They are Event Bus and Event Topic. You can use Amazon EventBridge to build Event Bus, and you can use Amazon Simple Notification Service or SNS to build Event Topic. And you can integrate Amazon SNS and Amazon SKS to build a powerful PubSub system. To distinguish when to use EventBridge and SNS, let us help you with this simple guidance. Amazon EventBridge is recommended when you want to build an application that reacts to events from SaaS application, AWS services, or custom application. While on the other hand, Amazon SNS is recommended when you want to build an application that reacts to high throughput and low latency events. EventBridge uses a predefined schema for events, and it helps you to select and filter events, while SNS topics are agnostic to the event schema. So let's see Amazon EventBridge in action.
In this demo, we're going to see how Amazon Event Bridge can solve the systematic synchronous API design challenge by changing the architecture with leveraging Event Bridge as an event router to handle the asynchronous communication between services. So this is how it looks like. Whenever order service receives requests, it's going to publish an event called order created to Event Bridge. Event Bridge will then push the event to respective services which are being the target for the particular event. Furthermore, few of the services will publish their own event, and so EventBridge will handle and push the event to the target services as well. Additional event that we're going to create is fulfillment completed by fulfillment service, which will be consumed by logistics service. So the idea is to have a complete data flow whenever the system receives order creation. Now, these are the Lambda function that I use for this demo. You might notice that I've added few additional services, and these services will be used in this demo to demonstrate how scalable and robust if we build a microservices with asynchronous communication with event router. So it's more complex compared to our previous demo. One thing that I like to emphasize is none of these functions know the existence of each other and no link whatsoever. All the communications will go through EventBridge as this function publish their own events. Okay, so moving on. The first question is how to publish the event to EventBridge. Now, this is a snippet code on how you can use AWS SDK, and this one is written in Python using Boto 3. It's really straightforward. You only need to call putEventAPI and then fill the parameters such as source, detail type, and event bus name. The detail variable holds our payload, so your data will go there. And all of these parameters could be used when we want to define the rule in Amazon Event Bridge. Now let's see how I configured the Event Bridge to handle the event. Let's go to the Rules section and select the Event Bus. On this page, you can see that we have few rules for each service. We have Fulfillment Service, Invoice Service, Logistics Service, and Notification Service. Let's take a look into one of these rules. One of the most important components in EventBridge is event pattern. Whenever it receives an event, it will match the event with the pattern that you have defined before routing the event to the target. Now in this context, if the detail type contains fulfillment completed, it will go to the logistics service, which is exactly what we want to have. So whenever the line items are fulfilled, it goes to logistics service to deliver them to customers. So if we go to fulfillment function, we can see this function publish the fulfillment completed to EventBridge. There's no downstream call to logistics service, it only publishes an event. And also, let's change the sleep time to 30 seconds, same with our previous demo, and to simulate the fulfillment service takes 30 seconds to complete one request. Similarly to our previous demo, the flow is started whenever we hit an API request, and the order service is our public API and integrated with Amazon API Gateway. So if we open this endpoint link, it will give us HTTP OK status code and an empty response. So let's test it out. This is our dashboard. Nothing too fancy over here. It's just to give us an info from our backend whenever it completes processing. So when it completes something, it's going to update this dashboard. Whenever we make an API call to order service endpoint, the order service will publish an event to invoice service, so it could send the invoice to the customers. The event that the order service publishes, it will also be consumed by the fulfillment service. Now, remember that fulfillment service takes a bit of time, around 30 seconds to complete the request. And once it completes the request, it's going to publish another event, which is logistics started, and it will be consumed by logistics service. And that will be indicated in this column that it's shipping to customer. Okay, cool. So let's start this demo. Let's use artillery tool again to create 100 requests. As you can see, the order service is now updating. And invoice service is being called and send the invoice as well. Good. Now the fulfillment service is trying to complete the job. And you notice once that the fulfillment completed, it's shipping to customers as well. And now all requests were handled properly, no timeout, quite fast I should say, and everyone is happy. And that's how you use Amazon Event Bridge to choreograph asynchronous communication between microservices.
So let's take a look at how EventBridge works. It all starts with an event source. This can be any one of any AWS services, your custom applications, or SaaS applications. So when you use a SaaS application integration, there is a special resource called Partner Event Source that provides a logical connection between the partner systems and your AWS account without the need for provisioning and managing cross-account IAM roles or credentials. At the core of Event Bridge are event bus. If you're familiar with the CloudWatch event default event bus, and this is exactly the same thing, except you can create your own custom event bus as well as a dedicated event bus to ingesting partner events. Once you have an event bus, you can associate rules with it. Rules allow you to match against values in the metadata and payloads of the events ingested and determine which events should get routed to which destination. We mentioned this earlier and just want to reiterate again that by using Amazon Event Bridge, we can expand event sources, and that's not limited only to AWS services, but it could also having third-party integration. With Event Bridge, you can easily integrate your application, for example, with Zendesk, with Datadog, MongoDB, Sugar CRM, Auth0, Segment, and more are coming. We'd love to think that with this kind of integration, it makes more easy and seamless for developers to subscribe to standard third-party events that you might already use. At this point, we've established a foundation on event-driven architecture and how to implement with AWS services. But the next thing that we really need to discuss whenever it comes to event-driven architecture is how do you manage the event types? As your application grows, you have more features, more services, and definitely more events created by producers through routers and for consumers. Now, this is a non-trivial task to do, because as it grows, your system more interconnected through events, and you need to spend more effort on defining the right event structure to produce and finding the right events to consume, but also understanding the structure. Like for example, what is the event structure for order created? How is it differ with order cancelled? And how if I need to react on payment refund event, and what do I need to send for subsequent event? Because the nature of producers that they are decoupled from consumers, they have their own autonomy to define the particular event. And in this decentralized communication, it's really a good idea to have a centralized event structure management. Introducing Schema Registry and Discovery, which is now in preview. The Amazon Event Bridge Schema Registry stores event structure or schema in a shared central location and maps those schemas to code for Java, Python, and TypeScript to make it easier for you to use events as objects in your code. Now, the cool thing is schema from your Event Bridge can be automatically added to the registry through the Schema Discovery feature. And for those who are using JetBrains products and Visual Studio Code, you must be happy to hear this, as it has an SDK toolkit to connect and interact with the Schema Registry. So how does this work? To react to events in their applications, developers need to know the event structure or schema. The process of finding events and their schema is typically manual. Developers have to look through the documentation or talk directly to the events developer. Now, the Event Bridge Schema Registry makes accessing schema easy by centrally storing schemas generated by all your event sources so any developer in your organization can access them. You can also download code bindings, which allow you to represent the event as an object in your code and take advantage of IDE features such as validation and autocomplete. You can download code bindings for programming language and use this code in your IDE via the AWS Toolkit or in the AWS console. When the Schema Discovery feature is turned on, all events sent to an event bus are automatically added to the registry, so there's no need to create schemas manually. I'd also like to highlight the importance of state, because in any kind of architecture, each of our services need to interact with another service to complete a specific workflow. And by understanding this concept, it will definitely help to complete our microservices with event-driven architecture. Workflows are made up of a series of steps, with the output of one step acting as an input into the next. And if we think about it, most of API requests is actually a subset of this so-called workflow. In e-commerce, we have a workflow to complete order, which might include checking the inventory, processing payment, updating inventory, sending notification to user, and send job order to logistics service. So how do we track the state between all of these services? How do we make sure things are executing in the right order at the right time? We need a state machine. In simple terms, we need a way to orchestrate the different workflows between all of these services. Set timing on tasks, interrupt execution, have tasks send heartbeats, and monitor and audit at fine granularity. Many applications contain workflows that must execute tasks in a reliable and repeatable sequence using independent components and services. Before step functions, customers who automated business processes had to spend weeks to write and then manage complex custom workflow code and interfaces. Now, our customers use AWS step function to add resilient workflow automation to their application. Workflows on step functions require less code to write and maintain. Step function integrates with AWS Lambda, which makes it easy to add Lambda tasks to workflow, such as calculating a credit score as a part of loan application workflow or creating a customer account as part of a subscription workflow. Developers can connect and coordinate various AWS services, database, and messaging service in minutes without writing any code. Now, this new service integration simplify and speed delivery of solutions for workloads such as order processing, report generation, and data analysis pipelines. By integrating AWS Step Function and AWS Lambda, it makes really easy to coordinate the components of distributed applications and microservices using visual workflows. Automatically triggers and tracks each step and retries when there are errors, so your application executes in order and as expected. It also logs the state of each step, so when things do go wrong, you can quickly diagnose and debug problems. And you can also integrating AWS Step Functions into your event-driven architecture to manage specific workflows and reuse the existing Lambda functions that you have. So at this point, we have covered the basic concept of event-driven architecture and AWS services to help you. We have Amazon Event Bridge to help you as an event router and third-party SaaS integration. We have AWS Step Functions to help us coordinate our business workflow. And we have AWS Lambda as our serverless compute. So let's see how all these components can work together in our next demo.
In this demo, we'll demonstrate how we can use Amazon Event Bridge to receive events from SaaS applications using partner integration and webhooks. The use case in this demo is how to process payment and support ticket. Freshworks is a complete customer engagement platform, and one of the products that they have is Freshdesk. We're going to use Freshdesk from Freshworks as a ticketing application which has a built-in integration with Amazon Event Bridge. And with this integration, you don't need to implement your webhook, configure your API, and doing validation before processing for any events. You just need to enable it from the SaaS applications and configure how you want your Event Bridge to route this event. However, you can also use Event Bridge for other SaaS applications using webhook. We're going to use Stripe as an example. Stripe is an online payment processing for internet businesses. And in this case, we're going to implement a webhook endpoint to receive events whenever there are events emitted by Stripe. So the story goes like this. Whenever there's a payment event triggered by Stripe, it will connect to our webhook, and our webhook will publish the event to Amazon Event Bridge. Amazon Event Bridge will then route the event to respective service, in this case is payment service. Once it completes the operation, the payment service will publish a new event called payment process to Amazon Event Bridge. Amazon Event Bridge will then route this event to AWS Step Functions directly to process the data and upload into Amazon S3 to be displayed in Amazon QuickSight as our dashboard. On the other hand, if there's a new ticket created in Freshworks, it will automatically trigger the Amazon Event Bridge because it has partner integration. Event Bridge will then route the event to support service as it needs to do a sentiment analysis to the ticket. Support service uses Amazon Comprehend to do sentiment analysis to get the sentiment whether the ticket is positive or negative. It's super useful to get the feedback from our customers so we can react quickly. After support service processes the event, it will publish an event called Ticket Process to Event Bridge. which EvenBridge will trigger AWS Step Functions again and upload to Amazon S3. AWS Step Function role here is to help us determine whether the data is a payment type or ticket type and do further processing before uploading the data to Amazon S3. Amazon EvenBridge can also integrate easily with other AWS services, and in this case is AWS Step Functions. Cool! So now we understand how this demo works. Let's see how we can easily integrate partner sources into Amazon EvenBridge. This is Freshdesk dashboard, and to integrate EvenBridge, all I need to do is to go to Apps Integration. I already have EvenBridge installed, and to integrate it is just search Amazon EvenBridge in the marketplace and install the application. Once it's done, you'll see that there's a new record in Partner Event Sources. And once that you have it, you need to associate with Event Bus, and EvenBridge will create a dedicated Event Bus for the integration. Now we have dedicated Event Bus, and next thing that we need to do is to create a rule. To create the rule, specify the Event Bus, and for the event pattern, choose the service partners. There are plenty of partners that you can integrate in this list. And for this case, let's choose Freshworks. And after that, we need to define the target, called support service, a Lambda function to handle the event from Freshdesk. And click the Create button to create this rule. As we have Freshworks integrated with Amazon EvenBridge, let's see how we can integrate Stripe. This is the Stripe dashboard, and I've built a webhook endpoint to integrate any events triggered by Stripe. And this is the Lambda function that will handle Stripe event. Whenever it receives an event from Stripe webhook, it will publish an event, payment received, into Amazon EvenBridge. Let's create a rule for this integration. First, we need to go to Amazon EvenBridge Event Bus page. Select the Event Bus and click on Create Rule button. Then we need to define the event pattern. We want to have all events with detail type payment received is handled by this rule. And once that we have done this, we select the target, our payment service Lambda function. And we're done. With all set, let's test it out. First, let's start emitting an event from Stripe. This is Stripe dashboard, and I'm on webhook page in developers menu. What I need now is to click the Send Test Webhook button. Okay, now we have our event emitted from Stripe. Let's head to Freshdesk from Freshworks to create a ticket. I'm creating a new ticket here and saying such an awesome service and thank you. Cool. Now we have all events emitted from our SaaS applications. I believe that all the microservices already done processing, and now let's head to Step Function and see if it's done processing. So here we are at the Step Function dashboard. As you can see, we have two records of execution here, and both of them will succeed. That's a good news. Let's see the details. In the first state mission execution, we can see that it's processing the payment from Stripe and successfully uploaded into Amazon S3. Nice. Let's see the second state machine execution. For the second state machine, it's processing the ticket and successfully uploaded into Amazon S3 as well. Cool. Let's see if the files are generated in Amazon S3 bucket. Okay, so we are seeing files from Amazon S3. There are two types of files generated by our microservices, one for payment and one for support tickets. And from this data, we can create a visual dashboard using Amazon QuickSight. And this is how our dashboard looks like in QuickSight by getting data from Amazon S3. And that is our demo to help you understand how to integrate SaaS applications with Amazon EvenBridge. With this integration, it unlocks many possibilities. You can use data from your SaaS applications to trigger workflows for customer support, business operations, and more.
So that's our take on event-driven architecture. It's our hope that by implementing event-driven architecture, it helps you to build a more reliable, resilient, and scalable systems so you can continue to experiment and be more agile with faster innovation to give more value to your customers. Thank you for attending. I hope you enjoyed this session and we had fun together exploring how to architect event-driven with AWS. We really appreciate your feedback so that we can better understand the topics and services you would like to know more about. So please do take the time to fill out our survey and let us know what you think. Once again, thank you for tuning in. I'm Donnie, and see you next time.
As a solution architect, having an AWS certifications allows me to measure how much I know about AWS solutions. I would recommend the AWS training classes because they are able to offer you information that is direct, comes from AWS platform themselves.
I started with Solution Architect Associate and then SysOps Administrator Associate. My journey towards SysOps Administrator Associate came out when I was trying to build a solution. Then suddenly, it came out like it is going to cost me a huge bill. That's where the SysOps Administrator Associate gives that kind of knowledge. Day to day, most of the administrators spend a lot of time on fixing the application issues, where the SysOps administrator, particularly on a AWS platform, will give much more insights how to troubleshoot and fix the application side. So definitely it's worth spending some time to do the multiple certifications.
Professional level certification is quite challenging to get. It definitely validates a person who has actual skills. And I would suggest to take it to engineer who really think he's at that level, when he can prove that he can work on quite challenging problems.
I'm Ulysses Nagi, Director for Enterprise IT. Our role to the business is to build, create, and implement solutions to give Voyager Group the best tech environment so we can all innovate. Voyager Group has been an AWS customer since 2014, and today we are already using more than 50 AWS services across various businesses like EC2, S3, RDS to Redshift for data lake, and Lex to Lambda for chatbot platform that is also integrated to social media touchpoint, where transactions are streamed to CRM-based management. Our business is in a better position to constantly innovate and support better customer demands. At Voyager, our goal is digital and financial inclusion provided by digital. We do this by building innovations that matter to their everyday lives. Our focus is the customer. Through our main platforms, we offer consumer and enterprise solutions. On the areas of payments, digital lending, Voyager's award-winning technology platform support the following digital services. PayMaya is the most recognized prepaid payment wallet service, enabling Filipinos to shop online, pay bills, buy load, and send money. PayMaya Business is the largest mobile acquiring service, enabling enterprise of all sizes to accept digital payments. Smart Padala is our domestic remittance. Lender is our digital lending platform. Freenet is our rewards app for free access to the internet networks. We live and breathe technology, and it is very much part of our DNA. In implementing ERP that is digital business configured, we look for a technology platform that has proven performance, supports scale-up, and can reduce IT complexities. By using AWS, our engineers can move ahead at maximum speed without much provisioning and maintenance overhead. On the security aspect, including regulatory compliance, we take it very seriously as part of our solutioning process to ensure data is protected. Recently, together with PLDT, we welcome new investors led by KKR, Tencent, and ASEAN. This was the biggest fundraising for a tech company in the Philippines. We're quite excited to further accelerate digital and financial solutions through our platform. We'll be moving quite fast, but we will move even faster. SAP S/4HANA Impact is designed to run in the cloud at peak performance. We use AWS because of its interoperability or cloud implementation approach, and flexibility to integrate with other corporate information systems in a multi-application environment. For our processes on customer acquisition, data lake, HR platforms, and many more. That's why we use AWS together with SAP to enable Voyager Group with technology platform that offers quick availability, faster deployment cycles, flexibility with shortest path to production, and built-in cloud security framework and business continuity.